Okay, so the last little new piece in this unit. So this unit that started back with two-dimensional collisions that went to conservation of momentum and energy with the buddies on the hill rolling down and hitting something, and the darts and the bullets swinging pendulums up, and then we went to simple harmonic motion. So now the last new piece is called the period of a pendulum. If we were in school, I would be saying, so what day would you like to test on? Obviously that's not happening, but it does mean that I'll be posting a practice assignment that you can use for all of this, just to see if you got it. But before then, the last new piece is the period of a pendulum. So if we think of a pendulum, like in a clock or something, right? It has a long string of some length with a mass hanging on the end. And it swings up to its highest point, and then back down and up the other side. If you think about the way it repeats its motion, you might think, hey, this is like a simple harmonic oscillator. It's repeating its motion back and forth over some period of time. This is length L here. And we'll make this a theta. But if this is a simple harmonic oscillator, then what would be its restoring force? So when it's up here at its highest point, what is it? What's the force that's trying to get it to come back down? Because remember, a simple harmonic oscillator must have a restoring force. So to figure that out, we need to look at what are the forces acting on this ball and this pendulum when it's at this spot. Well, there's a tension in the rope or whatever the cord is on the pendulum. And of course, there's our good friend, good buddy, gravity, Fg. And so if we take a look at Fg, it has two components. It has a component, Fgy, acting opposite the Ft, and assuming that this ball isn't moving along this line, then Ft and Fgy must be equal. And it has a force, Fgx, a component Fgx, and it's the Fgx that's acting as the linear restoring force. This theta and this theta would be the same because they're parallel lines, right? And these two coming down are coming straight down these two lines coming straight down are parallel, and this line is the same, and so the two thetas have to be the same. So if we take a look at Fgx, it's the opposite side of this little triangle. So it's going to be mg sine theta. And if the two thetas are the same, we could draw a line here, x. And so sine theta on the big triangle would just be x over L. And so if I sub this into my Fgx then is just equal to mg x over L. So we're saying this is our linear restoring force. So this is our F in that equation that we looked at the other day and that we looked at last year, F equals Kx. So Fgx is the F, X must be the X, so this mg over L must be our K. And so we're trying to find the period of a pendulum. If we go back to the period of a simple harmonic oscillator, so T equals 2 pi root m over K. And what we just found that for a pendulum, K is like the mg over L. So where the K is in the period of a simple harmonic oscillator, fill in mg over L. Dividing by a fraction is the same as flipping and multiplying. So 2 pi root m times L over mg. The m's are going to cancel. And the equation that we end up being left with is T is equal to 2 pi root L over G. This is the period of a pendulum. Okay, now an interesting thing is, notice it doesn't matter what the mass is. I could hang a marker on the end of this pendulum and swing it back and forth, or I could hang a person on the end of this pendulum as long as the length is the same and as long as we're at or near the surface of the Earth at the same spot, the period won't change. Now, how high it swings up will change, or how much force I need to get it started to go will change, right? Depending on who I have hanging on the end or a marker. But the actual amount of time it takes to go over and back, the only thing that's dependent on, if you're at the same spot, is the length. So if you think about it, you might think, but wait, what if I pull it up higher? If I pull it up higher, the period will still be the same, it'll just travel faster. If I only pull it out a tiny little bit, it'll still take just as long to go over and come back because it'll be going slower. So the higher the amplitude, the faster it will go as it passes through the rest position, but the period will still be the same. So the period is t is equal to 2 pi root L over G. And so there are some very pathetic questions in your textbook on page 614. And it's numbers 5 to 8. In one of them, you actually need to know the moon. If the period of the pendulum moon, what would be the acceleration due to gravity on the moon? I think it's on page, I'm going to say either 133 or 134. So when you're doing that one, check out page 133, 134. That's where the acceleration due to gravity on the moon is, okay? I forget which page it is, but it's one of those. All right, so page 614, numbers 5 to 8. And on your sheet, you have 2 questions left. And they're with the simple harmonic oscillators. They're numbers 7 and 8. So try those 2 too. All right, and that will end the unit. We'll go over these for the next day, and we'll start horizontal projectiles, which means I'll post the assignment as well so that if you're bored, you can work on it, the practice assignment. All right, have a good one.